And so from here, I would like to introduce our speaker for the night. So I asked for a brief bio today, and he sent me a full page, which I'm not going to read today. But I will say that Dr. Tony Noble, who is my boss's boss, he's the scientific director of the McDonald Institute. He has quite the history. So he did his bachelor's in physics and math from the University of New Brunswick. Before he went and did his PhD, before he did his PhD in particle physics from UBC. Then he worked as a postdoctoral fellow doing research at CERN before moving on to the University of Ottawa in Triumph. And then he came to Queen's University in 2002. But between then, he spent a significant amount of time working with the SNO experiment, the Sudbury Neutrino Observatory. And then he was a major player both on that team, which ended up winning the Nobel Prize, but also in expanding the Sudbury Neutrino Observatory into a SNO lab, which is now a world-class facility up in Sudbury, 2 kilometers underground, where we do amazing science. And it's now, instead of having just one experiment, it has maybe a dozen. And so today he's going to take this opportunity to talk a little bit about those experiments and science. So please, let's welcome Dr. Noble.
So it's amazing how people say nice things when you pay them. So I'm just going to get set up because we were flipping computers around, and I'm going to try something I've never done before, which is to try and run 2 screens simultaneously, one with my phone wirelessly and one on the computer. I didn't get a chance to practice, so it's going to be interesting how this all works. So let's see. In principle, I come back to the phone, I find a slideshow. I'll come off it. It's asking you to sign in. All right, cool. Okay, so meanwhile, I got to get this computer going. So while I'm getting this set up, I'll ramble a little bit. So I know there's a lot of students in the audience, and the answer is no. They asked several how many points they get if they attend my lecture towards their first year course. Okay, so what do we see here? Okay, so what you see here are 2 different slides. It will get better. But they're actually slightly different. This is what they asked me to talk about, exploring the invisible universe. And this is what I said I was going to talk about. And they're slightly different. But my goal here is really to introduce you very briefly to dark matter, because it's not actually a very long story. We don't know very much about dark matter. And but then, what is the evidence? What actually leads us to believe there is dark matter in the universe? And give you a feeling. So I'm an experimentalist. I'm trying to discover dark matter. And before I tell you how poorly we've done, I want to tell you how hard it is to make an experiment. So so what we know about dark matter, as I said, is not very much. And if you know this story about the man who has to roll a rock up the hill for his entire life, and then it rolls back down just as soon as he gets to the top. That's how we feel often in dark matter. It's been a long road, but we are actually making good progress. But what do we know? So I would say I'm going to try and convince you in a minute that we have irrefutable evidence that there is dark matter in the universe, and I'll try and go through the arguments for that as the next piece on the talk. But so far, the only way we have observed it is because it seems to influence things gravitationally. So it has an impact inside galaxies and structures that we see in the universe. We haven't actually seen it here on Earth, and that's what we want to try and do, to learn a little bit more about its properties. So we don't know very much, but we know it has to be neutral, non-charged, not like an electron or a proton, because otherwise it would be really easy to see. Things that have a charge are really easy because they interact with matter in a very straightforward way. So we think it must be neutral. It has to be massive, because after all, that's how we see it, is through all its gravitational effects. It has to be long-lived because all of our models at least suggest it was made during the Big Bang. And so that's 14 billion years, and it hasn't gone away yet. So in principle, it doesn't decay very quickly. It should be still around. and at best weakly interacting. And I'll say a little bit more what I mean about that, but there are different forces in the universe. Some are strong, some are weak, and this is very weak, which makes it very hard to detect because it's very improbable that it interacts with anything. Okay, so the evidence for dark matter. So a couple of years ago, people would normally point basically to one thing that they would say was evidence for dark matter. I just put 4 up here now, and I'm going to talk about them a little bit. And so these are the galaxy rotation curves, and I'm going to explain what those are in a little bit. There's something called gravitational lensing, which I'm not going to talk about, but it's a really interesting way of measuring mass because light bends around heavy objects. And so if the dark matter is there and it's heavy, the light will bend around it and you'll see suddenly this lensing effect, and that's what we're seeing here. In this case, it's lensing around a large galaxy, but if you had a large clump of dark matter, then you could detect the presence of dark matter that way as well. There's something really neat called these galaxy clusters. So you take a cluster of galaxies and you allow them to collide. When they collide, the gas all stays in one place, but the dark matter keeps moving. And through gravitational lensing, you see the dark matter ended up out here when the gas stayed in the middle. So these things collided and then separated. And you can see the separation of the two components. And there's no light out here in the blue part where all the mass is, where the dark matter is. So that's one thing. And then there's the cosmic microwave background, which is a little more challenging to figure out how that tells you something about dark matter, but I'm going to try. Okay, so let's focus on these two, galaxy rotation curves and the cosmic microwave background. Okay, so we'll start with rotation curves. If you were to take the solar system, because we understand the solar system very well, if you were to take the solar system and think about all the planets in the solar system, some of them are quite far away from the sun, some are quite close to the sun. In fact, I should give that to the students who ask for the free marks. I should get them to derive the equation, because it is actually rather simple, and we have a midterm on Thursday. They should be able to do it. If you write down that equation, then you get a very strong prediction of how the velocity should depend on how far away they are. So when you're really far away from the sun, you're going very slowly around the sun. When you're very close, you're actually whipping around the sun pretty quickly. So that's the prediction using this very simple formula. That's the formula. That's the gravitational constant, just a number, the mass of the sun, and the r is how far away it is from the sun. It's very, very simple. And if you plot it, that's what it looks like. If you now ask, okay, is it any good? I've put down here all the different planets. Right? So, and you'll see that it is actually pretty impressive. All of those things fall exactly on the curve, and they really shouldn't, in fact, because this assumes they're going around in a perfect circle. They're not. They're in elliptical shapes. It assumes all the mass is at the center of the sun, but of course there's some mass out there, Jupiter and Saturn and so on. So there's a small correction, but it actually works rather well. And so as I say, you get this more or less perfect agreement. There's some astronomers in here, so I know that Pluto's not actually a planet anymore, so we'll solve that. And I should mention Mercury. Just because it's on my slide, perhaps people have heard there might be, I think it's sort of tentatively off at the moment. Well, there is going to be a transit of Mercury on Monday morning early, and we had planned a big event to allow people to come down, look through solar telescopes, and so to see the movement of Mercury across. The weather is predicting 10 centimeters of snow, which is not exactly ideal weather for looking at the sun, but we'll see. So keep your eye open. There might be something that happens there. Okay, so I want to compare this now with another rotation curve. And so now instead of looking at the solar system, I'm going to look at the entire galaxy. So the scale is different. And this is now in kiloparsecs, which is huge. Here's the Milky Way galaxy. And we're going to look way, way out here, because although there's not much out here, there's still some stuff out here. And we can map what the velocity is. And if you do that, what you find, I don't know if this is going to work. Let's see. Oh yeah, look at that. Okay, so that's what we see. And the galaxy is different from the sun because obviously the galaxy is huge and all the mass is not at the center, so we don't expect it to look quite the same. The sun, oops, which one? This one. The sun is part way out, and so it's actually hard to measure these because when you're in the middle of all the cloud of dust and other stars and stuff, measuring the velocities of things at the edges is quite hard. But you can do it, and that's what you observe, but that's what you expect. You expect, because of the same effect, once you get outside the galaxy here, then things should get very slow, because all the mass is inside. It's just like this. Once you get away from the sun, the velocity goes down. So that's what we expect. That's what we see. Something is really wrong. And the explanation for this is that, well, I said we were outside the galaxy, but we really aren't outside the galaxy if you include the dark matter. If you include the dark matter is this huge halo filling up all this space. And so, of course, the curve looks wrong because we haven't accounted for the dark matter. So that's why I say, just looking at these rotation curves, and there's tons of them. You can look at galaxy after galaxy after galaxy, and you see all of these things. The rotation, you expect the rotation to drop off, and it doesn't. Okay, so in a way, this is the other way you can think about it, and I'm sure you've all done this. You've been in a playground where you have these roundabouts, and if the roundabout is going very fast, then the people on the outside are in danger. So the cowards all move to the inside and hold on to the post. Right? This, I'll just humor you with this, if it works. Oh, took too long to start. See if it'll go. Come on. Why is that not going? Yeah, I heard it for a second, right? Let me back up one slide previous and see if we can get it. See, I think what I did was... So now watch. Well, I like two things in here. One, this kid. Over here or something. Wow. The guy kind of looks at him and then, oh yeah, whatever, get back. But that's what happens when you're on the outside, right? It's too much, the velocity is too high, you get thrown out. And that's what should be happening to our stars that are on the outside of the galaxy. They're going too fast. They should be thrown out of here, but they're not. Something is holding them in place. Okay, so let's talk a little bit about now the next topic, which is the cosmic microwave background. So in the early universe, we think the universe was quite small and very homogeneous. So I mean, the material was all equally distributed, so I tried to draw that. Just, here's the early universe, and everything is symmetric. It's just completely homogeneous, uniform distribution. That was, I picked a number of 300,000 years old for a particular reason. If you looked at that, if you were able to see inside that, what we want to understand is how did the universe go from that distribution to what we see now as we advance time. We see something very different. It doesn't look very uniform anymore, right? We've got galaxies, we've got clusters of galaxies. It's very, very lumpy. Now this is a lot later. This is 14 billion years. That was 300,000 years. But as time went from there to there, something happened that made the universe change in terms of its structure. We've tried to understand how that happened and what causes that. So, and then of course, how's that related to dark matter? That's what you guys are interested in. So if you looked at the very early universe, then what you would find is it's so hot that the things that are normally the atoms, so if you had a, normally draw this as, say, a proton with an electron going around it, it's so hot that electron can't stay contained there, and it just flies off. And so the electron is flying off everywhere in space, the protons are bouncing around, it's just this ionized plasma. And in that situation, light doesn't get around to getting out. It can't travel very far. It just keeps hitting electrons, it hits charged objects, and it slows down, bounces, and so on. And so light doesn't get very far whatsoever. Okay, so in contrast, this was just a question I wanted to ask, and the astronomers in the room aren't allowed to answer the question, but it's how long does it take for light to go from the center of the sun to the Earth? Anybody know how long it takes light to get? Yeah?
Approximately 8 years.
8 years? Okay. It's 7 minutes? 7 minutes?
6 minutes.
8 minutes?
8 minutes. A lot of 8 minutes, 7 minutes, 8 years was maybe getting the units wrong. If you actually look at the sun, and I tricked you all, so you're all wrong, by the way, which is not an unusual thing when I'm up here lecturing and asking the students. The answer is not 8 minutes. The actual answer is something in the order of 1 million years. And the reason is, I asked you from the center of the sun. You're all right if I ask you what it takes for light to come from the outside edge of the sun. That's now free photons and they're just streaming towards us, and it takes about 8 minutes before they get here. But inside the sun, it is so hot that we end up again in this situation with this hot plasma, and the light cannot get out of there. It bounces around and it bounces around. It has a mean free path of about 1 millimeter. And this is pretty big, and it hits something, excites it, de-excites, and so on. And it just takes forever. So we don't actually know anything about the center of the sun from the light that comes out, because after all, it came from something that happened 1 million years ago and has bounced so many times it doesn't really carry any information. That's why, in fact, snow is so important, because the neutrinos, they don't care. They come right out of the sun, and the neutrinos are what we were using to observe the center of the sun. Okay, so there's my thing of the light bouncing around doing nothing. Okay, so those photons, wait a sec, hold that thought for a minute. So the universe is going to expand, and as it expands, it's like lowering the pressure, the temperature goes down, because the atoms are further apart, right? And so as it expands, at about 38 or 380,000 years, it got cold enough that those electrons and protons, which were all over the place, now became atoms. And so we had hydrogen with no charge anymore. That's a neutral thing. And now the photons inside there, they just go out and they're free and off they go. They escape. Right? And so now the light escapes freely, and it's been leaving so that event horizon, if you like, or that time in the universe at 380,000 years, it suddenly collapsed into hydrogen, and the light came streaming out, and we still see that light today. And so that's what this so-called cosmic microwave background is. If you like, it's kind of like a camera, using a camera where all this light is flooding into your lens, and we take a picture. It's a funny way of producing it, but this is how we do it in astronomy. This is a picture of the whole sky, and we're taking a photograph of that time of 380,000 years. It looks like there's a lot of structure there. In fact, it's not much. This is heavily enhanced to see very tiny differences. So these things are varying from maximum to minimum, if you like, by 1 part in 100,000. So it's very, very smooth, but it's not perfectly smooth. Okay. So if you look at that plot, you see there are some places where it kind of clumps together. So they're close together in angle. This here, these guys are all close together in angle. These guys are quite far apart in angle between those orange and those orange. And so you can plot that as a function of angle and say, what does it look like? And you get this interesting curve, which means nothing to you, or me, frankly. But what's really impressive is the green line is a prediction from theory. It doesn't use any data whatsoever. It's a prediction from theory. And basically, what goes into theory is a couple of things that aren't on here, but it includes how much dark matter is there in the universe, how much dark energy is in the universe, which we won't talk about, and how much normal matter is there, the stuff that makes up you and me and the planet and so on. And look how well the data fits. It's just incredible. It's perfect. You can't really get a better fit than that. And it's not really, if you change, you say, yeah, you know what, I don't want that much dark matter, I want 15% instead, then this doesn't fit at all, it just completely fails. And so the data is telling us from this picture of the early universe, which is actually telling us how lumpy the early universe was because of the presence of dark matter. And we can take that picture, so it's a photograph of the universe at 380,000 years. Okay, probably I'm supposed to do, who knows, I've lost track. let me go here. So Jim Peebles is a colleague of many of ours, a friend of ours, and he just won the Nobel Prize exactly 1 month ago. And so figuring out all of this stuff, which includes now that map that I showed you, which was saying how much dark matter there was, how much dark energy, he's the guy who figured all that out. And so I just wanted to put this up here because he was actually born in Winnipeg. He fled to the US, but that's okay. And he got the Nobel Prize a month ago, and we've been chatting with him. He is, of course, inundated with email right now. I think he had 1,000 within an hour of the Nobel Prize, all inviting him to come and give a talk. But he has said that he would like to come to Queens, and that, you'll get the joke, once the dust settles, he'll start planning out his tour. So we're hoping he'll come in March, and that will be another opportunity to hear a little bit more about cosmology. Okay. Yes, this one. So, so people are working really hard. It's difficult because you're trying to model the universe, right? And there's a lot of things in the universe, and computers aren't that powerful, so you make simulations that have a subset of the universe. And I don't want to show this whole thing because it's too long, but this is an evolution of the universe where they're looking at how matter comes together, dark matter, and so on. And it's fancified rotating around, but you see that all these things are producing strings and clumps and so on. And at the beginning, it looks kind of fuzzy. That's in the early universe. And if I could advance it, but I can't. Perhaps that probably restarted it, didn't it? Anyway, it's more or less goes on for a couple minutes, and it shows you, it gets more and more refined, and the clumps get brighter and brighter, and so on. So this is how we understand the universe actually to look. It's these long strings of sort of semi-connected things. You start collecting matter, big clumps in some places, and that's where matter is going to appear. And so I'm going to stop that and try and give you an analogy. So try and sort of imagine this thing, this big network of mass just sprinkled all through the universe, but with some overdensities and some underdensities. And I'm going to compare it to a spider. So if you think about a spider, you've all done this, run through the woods, and you can't see a spider web, and it's all over your face, and how pleasant that is. Right? So this spider, you can't see the web anywhere, but if you were to actually run past them, you would feel it, no doubt. So that's something you can't see, but we can detect it in some other way. On the other hand, if I were to spray that thing with water, so these aren't the same picture, obviously, but you get the idea. If I were to spray it with water, all the dew collects on the strands, and now it's pretty easy to see that. But when I'm not really seeing the spider web, what I'm seeing is the water on the spider web. So the analogy is, that's what we see in the universe. We see the normal matter, the baryons, the protons, all the things that make up us. But they have collected in these places because the dark matter exists there. And so the dark matter is what attracts all the baryons to collect and coalesce, and eventually you see as you look, zoom in on these things, you can see that stars are going to start forming because there's a whole cloud that has got very close together, and all the matter comes together and starts to collapse gravitationally and produce objects and so on. So it's very interesting that the models of the universe actually represent reality rather well. And so all of this goes together in terms of our ability to understand what the universe looks like right now. So now I'm going to tell you, as I said, I look for dark matter. Why is it hard? There's a couple of reasons why it's hard. First of all, we get excellent guidance from theorists. Theories of dark matter. I mean, that's how they make money, is to chase any shiny object and create a theory around it. But we have no idea what might be the fundamental. I mean, all we know is there's something out there that gravitationally attracts. And so there's lots of different ideas. We have tended to focus for various reasons in a type of dark matter, which we call WIMPs, which I'll get to in a second. But if you look at this plot, so these are taking some of the favorite ideas, and you say, okay, what's the mass of dark matter? At least tell me that. Well, it's somewhere between 10 to the minus 33 and 10 to the 18, so that's only 50 orders of magnitude uncertainty in what we should look at. And then you have to say, well, if the dark matter, if we're ever going to see it, has to interact, how well does it interact? And you say, okay, we can measure that as well. And here I have the probability that it interacts, something like 10 to the 24 to 10 to the minus 39. So another 60 orders of magnitude. It's just an enormous space. Where do you look? And so for various reasons, we have been picking areas where there are other physics motivations that would tell us that's a good place to look for some reason. And so we are spending a lot of time looking for what are called WIMPs. Physicists are a bit like that. WIMPs are weakly interacting massive particles. For a long time, there were people that thought, it's not particles at all. This is black holes, it's white dwarfs, it's objects that don't produce light, and you just haven't counted them up. And so those would be massive, active, galactic halo objects, which were machos. And so we had the machos versus the WIMPs. And I think we've ruled out machos, especially in the physics world, it's WIMPs. But that's what we've been spending most of our time looking for. So the second point is that they're weakly interacting. And so I want to understand a little bit about the scale, what it means to be weak interaction. It means they're really weak. It means nothing. I compare them a little bit to neutrinos. Neutrinos we do see, they are weakly interacting, and just to give you a feeling for the numbers, which is all I want to do here. So there's many tens of billions of neutrinos going through your body every second. So there's billions going through your thumbnail every second. They don't really care. They go right through your body. They go right through the Earth. In fact, of all of those things, those neutrinos going through your body, as tens of billions per second, for your entire life, you will probably never have one actually stop inside you. They just go right through. They don't interact very often. They don't notice the Earth. In fact, the figure of merit we use for neutrinos is if you took a light year of lead, which is big, and you shone neutrinos in one end, at least half of them would make it out the other end without ever having noticed that there was a light year of lead in the way. Right? So that's the problem. If you're trying to detect these things, and they don't interact very often, then it's quite difficult. So you have to build detectors as large as possible to increase the odds of seeing anything. Okay. The other thing is that the amount of energy that we're looking for is absolutely tiny. So what happens here is we have this very interesting slide, the nucleus, and a dark matter particle will come in, hit the nucleus, bounce off, and it's going to wiggle a tiny little bit. And that's going to produce some energy. So we say it has an energy of a few keV. That doesn't mean anything to most people, what a keV is. And so I calculated two other ways. So it's 1.5 billion times more energy than a mosquito when it's flying. Or if you had any of those treats outside, those Halloween treats, they have 5 times 10 to the 21 keV. We're looking for one. So they're about 20 orders of magnitude. So that's 100 billion billion. Yeah, 100 billion times less energetic than you would get from eating that Halloween candy. So they're really hard to detect because that's such a small amount of energy. So you're looking for something that maybe happens once every 10 years, and when it does, it produces such a small amount of energy, you'll never see it. And so we have to play tricks. And so the PICO experiment, which I'll tell you about a little bit in a minute, plays this trick where if I were to just give this rock just a little bit of energy, the result in my detector, let's say a line down here, is going to be rather dramatic. Right? I'm going to know that rock fell, even though I just applied a tiny, tiny little bit of energy. And so, that's not supposed to be there. You got in twice. Backgrounds. So, it's very rare. It's very small in terms of its energy. And we have this problem about backgrounds, which means that there are other things in life. A normal nucleus just sitting there decays in many different ways. It produces electrons, spitting out electrons. There's alphas. If it decays and produces alphas, it can kick out neutrons. It can kick out light in the form of gamma radiation. So all of these things are radioactivity that's happening all the time. Every material is full of stuff which is radioactive at some level, and that's a big worry. Because if that thing, one of those things comes out of there and then my nucleus just shakes a little bit, how do I know it shook a little bit because a gamma went out or it shook a little bit because a dark matter particle hit it? Very hard to tell the difference. So we have to get rid of all radioactivity. And I'll just give you a couple examples, especially for people here who eat bananas. A typical human has has potassium in it, about 140 grams of potassium. Potassium is naturally, why did that come? Anyway, that's bad. A typical human has 140 grams of potassium, and that is constantly decaying. And because, I don't know why that's, okay. Connect. Is it? It's as if it lost its connection somehow. Anyway, so you are all filthy radioactive because you eat bananas. And as I put here, if you stood 2 meters away from our detector, then the signal from your radioactivity would be overwhelming our detector by about 10,000 times the signal that we expect. Okay, now this is going to get annoying if that thing doesn't come back on. So as an example, another example, lead. We use lead a lot because lead is a really dense that stops things like gammas and things from getting into your detector. But unfortunately, unfortunately lead also has radioactivity in it. Normal radioactivity that it was born with, it's always there, except that it's produced by elements that when you make a brick, you take out. So if you make a brick, you get rid of a lot of the radioactivity, but some of the radioactivity that's left is no longer supported, so it will go away eventually, but it lives for about 250 years, and so, it's a long time to wait, 250 years, and you have to probably wait many times 250 years. But fortunately, while the Spanish were sailing around trying to sell their lead, the British were sinking their boats, and so there's a lot of lead that has been under the water since the time of the Roman days in these old galleons that were stocked with lead, largely used for ballast at the bottom of the boats. But that lead has been under there for 2,000 years, and so the radioactivity has disappeared. And so people go down and they collect this old lead from the bottom of the ocean. They cut all the interesting parts off and give it to museums, but the rest is kept and melted and used for people doing this kind of experiment. Okay, how do I get my signal back? I don't know why it's showing on my phone, which doesn't. I can show you all this, but it's probably not going to do very much. Let me see if I can just get this thing back quickly, because I've got some slides on here which I don't want to miss. That's not good. Let's see. Go to this one. Present. Timed out, maybe. What number do I need? 415. It change the code.
Say it out loud.
Yeah. I think it's going to come back. Okay, so found my phone again. Now I need to find the PowerPoint again. Ooh, okay, good. So one of the things we do is we go deep underground. And so why do we go deep underground? Is if you think about where a lot of our backgrounds come from, you've probably all seen the northern lights. These are particles that are raining down through the atmosphere. Well, they're being collected up in the magnetic field above the Earth, and they're being brought to the poles, and there they collide with the gases at the top of the pole. They're doing it everywhere, but there you see they're all focused at the top, so you see them a lot more. And it's because there are particles coming from outer space that are getting caught up there, but they're raining down on us all the time. And those would cause enormous problems for the experiment. So what we do is we build this facility called Snow Lab. And when you go to Snow Lab, you go deep, 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 deep underground. And so this was, when the time we were building the snow experiment, this was the deepest mine in the northern hemisphere. It's 2 kilometers down. Now they've gone a lot deeper than when we started. But we have a lab over here, so you go down 2 kilometers in the mine, you trudge through the mine, you end up in a norite rock, which the miners aren't interested in because it doesn't have any ore. And so we built our lab there. And so that's one of the things that we tried to do to get rid of radioactivity. Okay, so let me just see if we missed some pictures here. No, I think we did, but anyway. Okay, so I'm going to talk a little bit about PICO. So PICO is one experiment out of many experiments at Snow Lab that is trying to look for dark matter. And we do it in a very different way than most other experiments, which makes it kind of cute in the sense that we're using sound and the observation directly of the formation of a bubble, as I'll explain, to look for dark matter. Okay, so it's a bubble chamber. It's really what you wanted, which was a bottle of beer. In fact, rumor has it that this is how the bubble chamber was discovered, was by staring into flasks of beer. But the basic idea is that it's a superheated fluid. So if you took a normal thing of water like that and you heated it up, when you got to 100 degrees, it would start to boil, right? And you've all done that. You may also look on YouTube videos and see that if you take it and put it in a microwave, you can actually take the temperature well above 100 degrees. You can take water up to about 140 degrees, and it won't boil, if you have a clean enough mug. And so the students in here, I understand it's a problem, but if it's a really clean surface, so when you're cooking in a pan, you see the little bubbles start to form on the bottom, they kind of nucleate. They seed it, they start the boiling going, and that's just gas bubbles coming out of little pores in the bottom of the pan. But if your surface is smooth enough, it won't do that, and the temperature goes up. It's waiting for something to start the boiling. It needs a trigger of some sort. And so that's what we're doing. We're taking the temperature way, way, way above what's normal. And then a tiny amount of energy will come in, hopefully from a dark matter particle. And when it does, that will be the trigger, and the whole thing will start to boil. And then we have to control it once it's boiling. So we control when it's going to boil, when it's not, by changing the pressure and temperature and so on. That's the way the detector works. So this is a bit of a crowded slide, but the basic idea is we have a fluid here. This is all the mechanics of how we control pressure and temperature, which is irrelevant. But we have a fluid here. And we make it superheated by dropping the pressure. So I told you, if you take the temperature up, you can also do things by changing the pressure. So we drop the pressure, and then we wait. Here we're waiting for dark matter, and we wait, and we wait, and we wait, and then something happens, and suddenly it starts to boil. And when it starts to boil, it makes a gas bubble. That's what boiling is. It turns into a gas. So we can see a little pocket of gas here. So the cameras, they get excited, they take pictures and record and a lot of stuff. But it also makes a pop sound. And that's really important for our detectors. So we surround this thing with microphones that hear the bubble form. And then we measure pressures and all sorts of things. So, so this is a new detector that we're actually starting to commission. It's operational on the ground, but not quite ready for physics data. Just to give you a feeling of what this thing looks like. So this is a flask about as big as a person. It's filled with the fluid. It is now, not in this picture. It's filled with the fluid that we're looking for the dark matter to interact with. We put that inside a big pressure vessel so we control the pressure. And we have cameras that look inside and these microphones that listen. And we're just waiting for that really rare event when something comes in and creates a bubble. Now, you might think we're crazy for a variety of reasons. But, how do we know it works? Well, we have proxies. So we can take neutrons and we can shine. So these are like protons, except they're neutral. And we can take them and we can just shine neutrons in by putting radioactive sources close by. So this is a picture of our smaller detector. It's an older one. And if the video works, what you should see on this guy over here is that at some point in time, suddenly a bubble appears, right? And it's amazing. It's starting to boil. Now, we only take pictures for about 100 milliseconds, so about a tenth of a second, and then we've had enough, and we don't want the whole thing to boil, or it's a catastrophe. And so then we put pressure on it again. You don't actually see anything move, but believe it or not, that's going from about 30 psi to 300 psi in a fraction of a second, and it all happens to compress that thing back down again. So that's what you see. It's a bubble form, and so that's a proxy. That's not dark matter. We deliberately took a neutron and shone it in there. Now you might say, okay, that's brilliant. Now, if you see something, how do I know it's not a neutron? Because after all, if neutrons do exactly the same thing as dark matter, if I have a neutron come in that I didn't supply myself, which happens all the time, it's one of our biggest backgrounds. The thing about neutrons is they actually bounce around quite a bit. In that case, they only produce one bubble. But most of the time, they will bounce more than once. And so this is what it looks like more often, that you suddenly get this neutron that bounced all around inside my fluid and produced all of those bubbles. And then again, we take a picture for a tenth of a millisecond or hundredth of a millisecond, 100 milliseconds, and then we collapse them again so it doesn't destroy the detector. So that's good, because most of the time neutrons will not fool us. Now, you may occasionally just get one neutron goes in, hits once, and goes out. And so statistically, we have to look and say, well, most of the time neutrons do this. So if we have a source in neutrons, it's pretty obvious, because most of the time our pictures will look like this. And if we don't see any of these, then we don't have a problem with neutrons. Okay. So when this is kind of what our computer looks like, it says, okay, I saw some bubbles here. And it drew little pictures with red circles around where it saw some bubbles. You see the piezos. So these are our microphones. They saw something happen. And then the pressure starts to rise because the pressure is going up because the thing is boiling. Right? So we see all this evidence for something that happened. And we record it, and then we go back and we look where it came from and so on. We try and analyze it to decide, was it a background or was it something real? Okay. Go away. So to end a little bit, so PICO has been looking for dark matter for quite a while. So far we have failed to see anything, but that doesn't, remember that parameter space I showed you. It's an awful lot of work to look. This is a small fraction of it, so here's 3 orders of magnitude of mass. So we've been searching in this area, and basically what we have been able to do is say, well, within those, we didn't see anything, and so what it tells us is all of this pink area is ruled out. So if the mass is 100 GeV and it doesn't interact with this probability, all of that is gone. So we're slowly wiping out the parameter space, and we will continue to push down and explore all these different regions, try and push down to lower and lower masses to try and either hopefully discover dark matter, but if we don't, so right now we're building an experiment which is 10 times the size of the one that you saw being commissioned, and that will give us 10 times more sensitivity. And we hope to discover dark matter or start to rule out pieces of parameter space. And so for that I say stay tuned. In terms of radiation mitigation, so our alpha particles, it turns out, sound different than neutrons and dark matter. And I can show you a plot here of that. So just to show you that it's not radioactivity. So alpha particles, so this is something you don't need to know what it is. It's an acoustic power. So it's a measure of the signal from the microphones. And if you have alpha particles, they make this huge peak here. And if you have things that are like WIMPs, they make this peak down here. And so there's clearly a difference in the sound. And we understand why that is. It's the way the track is made through the fluid. They expand differently, and so the way they make sound is different. But nonetheless, we've been able to rule out alphas. Turns out that betas and gammas, so electrons and light, they don't bother us at all. They don't trigger our detector because we operate at a temperature where they won't bother us. And as I said, neutrons we can avoid as multiple scatters. So all of those things together means we have kind of eliminated the main backgrounds that annoy other people. And so we think we will be able to push this with a new detector 10 times. We won't have problems with backgrounds, and we'll be able to continue another factor of 10 down and keep exploring the space. As I say, it's a hard game, it's a long game, but that's where we're at. Okay, so I'm going to stop there and see if there are any questions. And I think, is it true that there's something happening? Well, I know there's stuff happening there, but I was told that even after all of this is over, some people are going to the pub And so you might want to try searching for your own dark matter there, and you can see that this dark matter has really caught on in clubs. There's just every type of dark matter that you can possibly think of. And so if you go to the mansion tonight, you want to explore that a little bit. And I'll take questions at this stage. Thank you. Except for my students, they're in first year, they can't.
Thank you very much. Do we have any questions?
It was one of the slides where it was, I think the universe was around 380 years, 1,000 years old.
Yeah.
And it was mentioning how the light could escape from the particles and they could actually form into atoms.
No, what I was saying was before that.
It was plasma.
Yeah, before that you have a plasma, and so everything, you have electrons flying all over the place. And the photons are mainly bouncing off the electrons. But at a certain time, the temperature of the universe got low enough that the electrons disappeared because they combined with the protons to form magnitudes. Now it's kind of empty space. They don't have these electrons all over the place, so they stream out at that point.
Why didn't the hydrogen atoms that were formed collapse down at that point?
Well, they're still very hot. We're still at
So that's why it kept expanding?
yeah, so the whole universe expanded. They are atoms, and after this phase, we go into sort of what's called the dark ages, where you just have these atoms all over the place, but they're not clumping together, so they're not making stars yet. There's no light, so the whole universe would have been very, very dark during that whole period. There's a question up there.
Is dark matter good for us?
It's good for me because it pays my salary. But the answer is that dark matter, there are probably something like, it depends on what the mass is and how many there are, but they're similar to neutrinos, which means there's probably about 400 dark matter particles in every something the size of a dice, about 1 centimeter cubed. So if you imagine just a little dice, there's probably about 400 dark matter particles in there, and completely going through you, and they've been doing it all your life and through the entire history. So they just don't interact. They go right through you, they don't touch you. And so they're not harmful in any way. And we can't think of any good use for them other than understanding physics.
So by eliminating all the known particles, what we found has been selected to be dark particles, so dark matters. But how do we know how do we identify if we found anything is dark matters, not some other unknown particles?
Yeah, so you're saying, how do I know it's not a background that I haven't accounted for or something, if I see something in my experiment? Yeah, that's very hard. And so there's a couple of strategies you can use. One, the way it works, the way it interacts will be very different depending on the type of experiment, or more importantly, the type of fluid you have or matter. So some people are using xenon, we use fluorine, different products. So if anyone sees a signal, the first thing is everybody will tune their experiment to try and reproduce it, but it will have to look a little bit different in their experiments, and all their backgrounds are different. It would be very unusual for all of our backgrounds to trick us in different experiments in the same way. So that's one thing. The other thing is the Earth is traveling with our solar system through the galaxy. And so that means we're going through a wind of dark matter. We're actually moving through it. And so if you really thought you saw dark matter, then one of the cool things you can do is, once you know it's there and you can optimize your detector, is when we are going around the sun, sometimes we're running into it, it's like running into the rain, and sometimes we're running away from it. And so the rate that we interact with dark matter in those two cases will be different. And so you could look at a difference in how much dark matter you see in the winter versus the summer based on this rotation of us around the sun. And so that will be a real smoking gun. We're not trying, people are trying to do that now already, but it's very difficult. But if you saw dark matter, that would be the next step. You would make your detector that much bigger to look for that annual modulation. Yeah.
So I know this is kind of looking further ahead, but could this, like the search for dark matter and the stuff you're doing for that, could you use kind of those techniques to eventually look for dark energy as well and what that is?
There are people who are trying to think about how to look for dark energy. It's probably different strategies and not these kind of detectors, which are really, these detectors are meant to see the interaction of a particle inside the detector, which leaves some kind of trace of energy. The way we look for dark energy is first to come up with some ideas about what it might be. And then, but there are certainly experiments around that are looking for that, but they're quite different. So I would say where this helps in many ways is that the techniques that we develop for these experiments are really pushing the frontiers of technology. And then what usually happens is we sweat for years to develop some new technology, and then someone brighter than us takes that new technology and runs and makes a positron emission tomography spectrometer or something like that technology, which benefits mankind. And so a lot of the techniques we develop end up in medical physics and things like that because they're quite useful. But somebody taking this application and applying it to the things.
So I think we have one last question up here, and then if more people have questions, then you can come down and talk with Dr. Noble afterwards. Or I think actually
there's one up there.
If there is one up here, we'll take that.
Oh, I think it is.
Do you have a question?
Oh, you were just had your arm resting. All right.
Here's our last
I'll ask a question. With normal matter, we've got 100 plus elements. Dark matter, are we anticipating it to be all one type of thing, or is there going to be a wide range?
Well, that's something that we ponder a lot. Right now, we are hoping to see some evidence of some kind of a particle. In the WIMP paradigm that I talked about, these weakly interacting massive particles, the reason they're favored is we live in a world where we have particles that are made out of quarks and things we call leptons, which are electrons. So you can think of it as quarks and electrons. They combine in various ways to make all the different elements. They make neutrons, they make protons. You put the neutrons and protons together. So as you said, we've got over 100 elements. There's a certain symmetry to that, which is broken in the sense that everything that has to do with the forces, it has a spin 1, and things that are particles have spin 1/2. So this refers to the way that they spin on their axis. It's a quantum mechanical thing, but it's not very elegant. So there's a new theory that came up that said there's another half of the universe that we haven't talked about, where we also have spin 1 particles instead of just spin 1/2. And that's called supersymmetry. And it predicts an equal number of particles to what we have today, and therefore you can also build all these other elements. And that's actually, it's the beauty of that symmetry mathematically that led to this sort of description in terms of WIMPs. If that's true, it turns out they would all be much more massive, and things that are massive tend to decay to smaller things. But there would be one particle left over that couldn't decay, because you have to still have some of this supersymmetry. And so you'd have one particle left, and that could be the dark matter. But there's no reason to think that the dark matter couldn't be a whole family of different particles, and therefore we'd have to start looking at their interactions and saying, ooh, so this type and that type and so on. Right now we're trying to get a hint of any kind of signal to pursue it, but you're absolutely right. It would be rather unusual to think that on this side of the line, in this part of the universe, we have all of these 6 quarks and 6 leptons and 4 different forces, and over here we have one particle. It doesn't really make sense. But right now, we're just looking for the interaction of something so that we can start to explore it, and then we know where to focus the experiments and so on.
If you find one, you look for others.
That's right.
Okay, so let's thank Dr. Noble again.